Hello YouTube! So today we're going to be talking about an example problem using work. Well, no, actually we're not using work, we're just using springs. Using springs. And in particular, springs can get kind of weird because if you're dropping something vertically or if you're dropping something at an angle, you might have to keep track of that distance that the spring travels, and it might be related to a height that the spring goes up or down, which means you have multiple types of potential energy to keep track of at the same time. So that in particular is going to be relevant for the one we're talking about today. Cat's auto feeder goes off in like 5 minutes, so they're not happy about this. All right. So in particular, looking at our setup, we've got something where we've got a block. It's starting up here at rest, and then it goes down and it compresses a spring. And that spring gets compressed by a distance of 5.5 centimeters or 0.055 meters before it stops. The hill has an angle of 30 degrees, and the thing has a mass of 12 kilograms. We're also told that for our spring, when we compress it by 0.2 meters, it goes back with a force of 270 newtons. So that could help too, and will. Location, I've taken this problem and broken down into a few things about how I'm going to think about it already. First off, I know that location 1, I'm just going to call the top, the place where it's at rest and at like its highest point. Location 2, I'm going to call the place where it stops down at the bottom. And location 3, I'm going to call the place just as it hits the spring, because question A is asking about the height at the point where it stops up on the hill. And question B is asking about how fast it's going just as it hits the spring. So first thing I look at, and I can say like, oh, I can figure this out pretty quickly, is I can figure out the spring constant using the amount of force and the compression distance, because the force from a spring is equal to negative kx. And if I want to find k and I have force and x, I just have to divide by negative x. And what that'll leave me with is that k is equal to fs over x, which is negative 270 over 0.02. Now, will this be negative? No. Something that I could go ahead and do is just ignore this negative sign and make this an absolute value sign. And that's something that actually the AP exam does for AP Physics 1. You just have to think about what direction it goes. And in this case, that'll serve us a little better, so we don't have to worry about that negative here, because we're not told which direction 270 newtons goes, so I haven't really been including that. So 270 divided by 0.02 is equal to 13,500 newtons. So for every meter this thing is compressed, it gives back a lot of force, which pretty much just means that we're not going to compress this thing a meter. Great. So now we have k, and k is no longer a variable. We can go ahead and use stuff with k when we're trying to figure things out. Cool. So I'm being asked about location 1. The place where I know more stuff about right now is location 2. I know that it stops at that point, and I know how much it compresses at that point. So what I can do is I can say that at location 2, well, I said the height there was 0. So EU is 0, and it's not moving, so EK is 0, both of which at location 2. And so I can say that 1/2 kx squared, the energy stored up in that spring, is going to be equal to the energies it has at the top. Well, there's no spring, and it's not moving, so mgh. what's nice about this is that our only variable here is h1. So I just have to divide each side by mg. And we'll get that h1 is equal to mg, 1/2 kx squared divided by mg, which is 1/2 times 13500 times 0.055 squared divided by 10 times 12. And I flipped the m and the g there. Which 0.5 times 13500 times 0.055 squared divided by parentheses, well, I can just do 120, gives me 0.17 meters. So our first spot on our hill is 0.17 meters above where we started. All right, so that's it for A. B is actually a little bit less straightforward. We're going to have to do some geometry as well. The big thing for B is that it won't be touching the spring anymore, but we actually can't ignore the spring. Because if we're going to try to find the velocity at location 3, we're actually going to need to use the height at location 3 because it's not at our 0 point anymore. So there's a few different ways you could think of this. You could think of this as falling from h3 to h2, meaning we use location 1 and location 3. Or you could think of it as starting at the bottom of the spring and getting launched up the hill to location 3. I think just for the sake of helping people get a little more comfortable with using the spring part, we're just going to use the spring part, but you could just as easily choose the other one and you would get the same answer because the energy is the same regardless. So the big thing here is that our x is our hypotenuse for a triangle that has h3 as the opposite with an angle of 30 degrees. Which means that the sine, if I take x sine 30, that'll equal h3. So what I can do here is I can say that the potential energy stored in the spring at the beginning needs to equal the kinetic energy it has when it launches plus the potential energy it has when it launches. And since I know that h3 is equal or related to x, and I know what x is, I'm also pretty much done with this one, but I do have to remember that little algebra thing, and I do have to remember to actually write out the squared. All right, next step here is going to be to get the velocity alone, so I need to subtract each side by mg times 8x sine 30 minus mgx sine 30. That'll give us that kx is equal to 1/2 mv squared. I need to multiply by 2 divided by m, and multiply by 2 divided by m. Once I've done that, just for the sake of rewriting this stuff so many times, I'll need to square root. And last time I left some stuff out of my final answer when I was doing the numbers, so I'll try not to do that this time. I'll have the square root of, and I'm going to distribute it because some of it's going to cancel, kx squared over m, distributing the 2 to cancel out the half and the m in there, minus gx sine theta over 2. So the mass canceled from this one, 2 2 gx sine theta. The mass canceled from this one, the half canceled from this one. And that'll equal v3. Great. And when we throw numbers at it, we should get the square root of, 13500 times 0.5055 squared divided by 12 minus 2 times 10 times 0.055 times the sine of 30. So, parentheses 13500 times 0.055 squared divided by 12 minus 2 times 10 times 0.055 times the sine of 30, close parentheses, to the half. And this calculator is almost dead for battery, but we've got that the 3 is equal to 1.7 meters per second. So sort of recapping everything before wrapping up. We used our known compression distance and known compression force to figure out the spring constant. Once we had the spring constant, we set up sort of a situation where we could have the energies at a few different places. Once we had the energy at those few different places, we could sorry, I got sidetracked by something else. Once we had the energy at those few different places, we could set up equations for that. We could say, okay, well, at our first location, specifically because we picked the height there to be 0 to make the math easier, would have worked just fine. If we had put the height somewhere else, we would have just had to figure out where this location was in terms of x to get our second height. But this was the lowest point, so I just made it 0. The location at the bottom just had potential from the spring. The location at the top, because it stopped, just had potential from gravity. And then we did a similar setup for our next place, where we have the potential from the spring at the bottom, which could have just as easily been mgh1. And that'll need to equal 1/2 mv3 squared plus mgh3. Honestly, mgh1 might have been a little easier because the masses would have dropped, so a little less writing, but that's pretty much it. So feel free to ask questions if you got them. I'll get this posted to YouTube. Goodbye, YouTube.